Welcome to another Explainer. I am absolutely pumped for today's topic because we're taking a mind-bending dive straight into the atomic world. We are going to look at a realm where everyday materials just completely push the boundaries of what we thought was physically possible. I mean, if you've ever thought that solid metal is just this rigid, unchanging block of matter, well, prepare to have your mind totally blown. We're exploring the cutting-edge reality of materials engineering today, and trust me, by the end of this, you're going to look at the world around you in a completely different way.
So I want to start off by asking you a question right out of the game. Have you ever seen a metal with a memory? Just think about that for a second. Imagine a seemingly impossible magic trick happening right in front of your eyes, meaning no matter how much you absolutely crush it, bend it, twist it entirely out of shape, just with a little bit of heat, it perfectly remembers its original shape and transforms right back. I know, it sounds like pure science fiction, right?
Okay, let's dive into this. Picture this. You take a normal-looking metal paperclip. You completely mangle it. You just bend it until it's this totally unrecognizable, crushed knot of metal. Then, you drop it into a simple glass of hot water. Instantly, literally, right before your eyes, it snaps back into that perfect original paperclip shape. It is absolutely wild to watch. But here's the secret. No, this isn't magic. This is exactly the incredible power of material science and metallurgical engineering at work.
All right, let's transition to the real science behind this in Section 1, the atomic architects, bending physics.
Now, what's really interesting about this slide is the stark contrast between what we assume metallurgy is and what it actually is today. When a lot of people hear the word metallurgy, they instantly think of traditional welding, right? Or maybe giant scorching iron melting furnaces with sparks flying everywhere. But look at the reality of it. Today's materials engineers are quite literally the architects of the atomic world. Imagine an engineer looking through a microscope treating atoms like tiny Lego pieces. They are actively combining elements in such precise ways to create materials that push those physical boundaries we just talked about. They aren't just melting stuff down anymore, they're building with the very building blocks of the universe.
And that brings us to the heroes of today's Explainer in Section 2, meet nitinol, the shape memory alloy.
So the crucial point is understanding exactly what these shape memory alloys actually are. And the most famous of these is called nitinol. I just love this concept. It's basically two elements, nickel and titanium, shaking hands and joining forces to become a superhero material. When you mix nickel and titanium together in just the exact right way, you get this unbelievable alloy that can actually remember its past life, so to speak. Let me walk you through the actual atomic dance routine that makes this happen, which is laid out in these 3 steps here. Step 1, you bend the metal. But here's the secret. When you bend nitinol, its atomic structure doesn't actually break or tear like a normal metal would. Instead, it undergoes a phase change, moving into a state called martensite. In this state, the atoms are basically just folding up. Then, step 2, you apply heat. And step 3, the atoms undergo another phase change, this time back to a state called austenite, and boom, they snap perfectly right back to their original places. The atoms never actually let go of each other, they just shift. And when that heat hits them, it's like the metal is stretching its arms and waking right back up into its intended form.
To perfectly visualize this, when you bend this metal, its atomic structure doesn't break. Instead, it folds up like an accordion. This quote captures the sheer, unbelievable resilience of this material. So, next time you think of bending metal, don't picture snapping a rigid twig. Picture an accordion compressing. The structure is all still perfectly there, just waiting to be expanded again. I think that makes this super complex atomic concept incredibly easy to visualize and remember.
Now you might be asking, how is this shape-shifting metal actually used to solve massive real-world problems? Well, let's get into Section 3, Real-World Superpowers, nitinol in action.
Let's start with an application that is highly relatable. Actually, it's probably something you or someone you know has experienced firsthand. Orthodontic braces. Yes, the braces on your teeth. When orthodontists use nitinol wires, they don't have to just manually crank and endlessly tighten them. Instead, they put the wire in, and the simple, natural heat of your own mouth acts as the trigger. Your body heat causes the nitinol to gently contract back to its original, perfectly engineered shape, which smoothly and constantly straightens your smile over time. It's brilliantly simple.
And it gets even more vital when we move to life-saving medical applications, like heart stents. Imagine a blocked artery inside a vein. Surgeons can take these tiny spring-like structures made of a shape memory alloy, compress them down incredibly small, insert them into the vein, and then, triggered by the environment of the body, they seamlessly expand and open up that blocked artery. It is literally doing atomic-level heavy lifting right inside the human body to save lives. And this brilliantly illustrates the ultimate futuristic application, NASA Mars rovers. I mean, when you're driving a multi-billion-dollar rover millions of miles away on another planet, you absolutely cannot afford a flat tire. There's no roadside assistance on Mars. So NASA uses these shape memory metals to create tires that literally deform when they roll over those jagged, brutal Martian rocks, and then they instantly bounce perfectly back into their round shape. No air, no rubber, no flat tires. Just pure materials engineering conquering another planet.
It really makes you step back and appreciate just how vital it is that we understand the materials around us, doesn't it? Let's zoom out to our final section, Section 4, Shaping the Future of Materials Engineering.
Let's move to and see how this builds across the timeline of human civilization. Look at this, from the Stone Age to the Bronze Age to the Iron Age. Notice a pattern here? Human history has quite literally always been defined and shaped by the materials we discover and learn how to manipulate. But look at Era 4, today. We aren't just finding materials lying around anymore. Through materials engineering, we are actively designing the atomic building blocks of the future. We are creating materials that solve problems our ancestors couldn't have even dreamed of.
Which leaves us with this final question. What weird materials should we look at next? The secrets of the materials world are all around us, just waiting to be uncovered, and we have barely scratched the surface today with Nitinol. I want you to stay curious. If you loved understanding the hidden mechanics behind the everyday world, make sure to hit that subscribe button. And seriously, jump into the comments right now and answer this question for me. Tell me what mind-bending material you want me to feature in our next explainer. Until next time, keep questioning how the world is built.